The universe, in its infinite expanse, bathes us in a symphony of light. Yet for much of human history, capturing this light, freezing a moment in time, remained a distant dream. The earliest cameras, rudimentary contraptions compared to today's digital marvels, could only capture the world in shades of gray. These monochrome images, while groundbreaking in their time, lacked the vibrancy and nuance of the world as we see it. The quest to capture the world in full color, to mirror nature's own palette, would drive decades of scientific innovation. Pioneering photographers, armed with bulky cameras and glass plates, could only dream of capturing the world in its full chromatic glory. Light, the very essence of vision, holds the key to understanding color. It travels in waves, each wavelength corresponding to a specific color within the visible spectrum. Red, with its longer wavelengths, occupies one end of this spectrum, while violet, with its shorter wavelengths, sits at the other. Between them lies a continuous band of colors, blending seamlessly into one another: orange, yellow, green, blue, and indigo. Unlocking the secrets of this spectrum paved the way for capturing the world in its full chromatic splendor. Physicists had long known that white light, far from being a single entity, was actually a composite of all the colors of the rainbow. The human eye, a marvel of biological engineering, perceives color through the interaction of light with specialized cells called cones. These cones, sensitive to red, green, and blue light respectively, form the basis of our color vision. The brain, acting as a sophisticated image processor, combines the signals from these cones to create the perception of millions of different colors. This trichromatic principle, the foundation of human color vision, would also become the cornerstone of color photography and digital imaging. Just as our eyes rely on 3 types of cones to perceive color, so too do digital cameras rely on a similar principle. By combining these 3 primary colors of light in varying intensities, we can create a vast spectrum of colors, mimicking the way our eyes perceive the world. At the heart of every digital camera lies a sensor, a silicon chip studded with millions of tiny light-sensitive elements called photosites. These photosites, analogous to the rods and cones in our eyes, convert incoming light into electrical signals. However, unlike our eyes, which have separate cones for each primary color, individual photosites are inherently colorblind. To capture color information, cameras employ a clever trick. They filter the incoming light, allowing only specific wavelengths to reach each photosite. Without color filters, this grid would only capture a monochrome image, a map of light and shadow. To infuse this grayscale image with color, each photosite is paired with a color filter, typically red, green, or blue, The most common arrangement of color filters on camera sensors is the Bayer filter, named after its inventor Bryce Bayer. This ingenious pattern, resembling a checkerboard with twice as many green filters as red or blue, mimics the sensitivity of the human eye. Since our eyes are more sensitive to green light, the Bayer filter allocates more green-filtered photosites, resulting in a more natural-looking image. This mosaic of color information, captured by the sensor, forms the raw data from which a full-color image is reconstructed. When light strikes the sensor, each photosite records the intensity of its filtered color, creating a mosaic of red, green, and blue values. This raw data, far from resembling a recognizable image, forms the foundation upon which sophisticated algorithms work their magic, interpolating the missing color information to create a full-color photograph. While our eyes are limited to the visible spectrum, cameras can venture beyond these boundaries, capturing wavelengths invisible to us. Infrared cameras, for instance, detect heat radiation, revealing hidden patterns and temperature variations. Ultraviolet cameras, on the other hand, can capture details obscured by visible light, revealing intricate patterns and fluorescent properties. These specialized cameras, extending our vision beyond the limitations of human perception, find applications in fields ranging from astronomy and medicine to security and art conservation. Infrared photography allows us to visualize heat distribution, highlighting temperature differences in vivid detail. Ultraviolet cameras reveal details invisible to the naked eye, such as fluorescent materials and hidden patterns in artwork. Although cameras have made remarkable strides in capturing color, their perception differs from our own. Our eyes, constantly adjusting to lighting conditions and interpreting context, perceive a wider dynamic range and subtler color gradations than cameras can currently capture. Moreover, human vision is subjective, influenced by factors like emotion, memory, and cultural background. While cameras strive for objective accuracy, our visual experience is colored by our own unique perspectives. The human visual system, honed by millions of years of evolution, possesses a sophistication that still eludes even the most advanced cameras. Our eyes, dynamically adjusting to changes in lighting and context, can discern subtle gradations in color and brightness that cameras struggle to replicate. Factors like emotions, memories, and cultural backgrounds all play a role in shaping our individual experience of color. The process of capturing color doesn't end at the sensor. Sophisticated image processing algorithms come into play, interpolating the missing color information from the Bayer filter and making adjustments based on factors like white balance and exposure. These algorithms, constantly evolving and improving, strive to create images that are both visually pleasing and true to life. The goal is to bridge the gap between the raw data captured by the sensor and the nuanced color perception of the human eye. Image processing software analyzes the raw sensor data, interpolating the missing color information from neighboring pixels and making adjustments based on factors like white balance, exposure, and color temperature. These algorithms strive to create images that are both visually appealing and faithful representations of the original scene. The invention of color photography revolutionized the way we see and interact with the world. From photojournalism to fashion, from advertising to personal memories, color images have an immediacy and emotional impact that black and white photographs cannot replicate. They transport us to distant lands, document historical events in their full vibrancy, and preserve precious moments in time, ensuring that the colors of our lives are not faded by the passage of years. Color photographs hold the power to transport us to distant lands, evoking the warmth of a tropical sunset or the cool serenity of a snow-capped mountain. They allow us to relive historical events as if we were present, feeling the energy of a political rally or the joy of a victory parade. And on a personal level, color photographs preserve our most cherished memories in all their vivid detail, ensuring that the colors of our lives, like the stories they tell, are never forgotten. The applications of color capture technology extend far beyond the realm of photography. In astronomy, telescopes equipped with specialized cameras capture the faint light from distant galaxies, revealing the secrets of the cosmos in breathtaking detail. In medicine, medical imaging techniques like MRI and CT scans rely on color to visualize internal organs and diagnose diseases. From mapping the ocean floor to analyzing agricultural yields, color capture technology has become an indispensable tool in countless fields, expanding our understanding of the world around us. Astronomers use color data from telescopes to determine the composition, temperature, and motion of celestial objects, piecing together the history of the universe. Medical professionals rely on color-enhanced images from MRI and CT scans to diagnose diseases, plan surgeries, and track the effectiveness of treatments. The quest to capture color with ever-increasing accuracy and fidelity continues to drive innovation in camera technology. Scientists and engineers are developing new sensors with higher resolutions and wider dynamic ranges, capable of capturing even subtler gradations of light and color. Artificial intelligence algorithms are being trained to recognize and correct color casts, further enhancing the accuracy and realism of digital images. As technology advances, we can expect cameras to capture the world with a level of detail and nuance that rivals and perhaps even surpasses the remarkable capabilities of the human eye. These advancements promise to unlock new levels of detail and nuance in color capture, allowing us to perceive the world with a clarity and richness that surpasses even the remarkable capabilities of the human eye. As technology continues to evolve, the line between the digital and the real will continue to blur, offering exciting possibilities for photography, filmmaking, virtual reality, and countless other fields that rely on the power of color to inform, inspire, and amaze.